Hi everyone, my name is Federica Rescigno and I'm a PhD student at the University of Exeter. Today I will be talking about the line of sight magnetic flux as a proxy for stellar activity, and in particular as a proxy for stellar activity for magnetically not so active stars like the sun. This work has been done as part of the Terra Hunting Experiment Polarimetry team and in collaboration with the Harps North Solar team. Now, let's get the basics out of the way. We know that in RV surveys, we use proxies of stellar activity to pinpoint stellar characteristics such as the rotational period. However, many of these proxies have been shown to not perform well at very low activity or in the low activity regime. We are going forward to look at stars for long periods of time to search for Earth-like planets. So we are expecting to see different activity regimes in the same star. So we need proxies that work just as efficiently at high activity as they do at low activity. At the same time, we know that most of stellar activity-induced variations in radial velocity are in a way directed or related to the stellar magnetic fields. So how about we use the information directly from the magnetism of the star? We know that polarimetry allows us to measure Stokes profiles and therefore longitudinal line of sight magnetic fluxes. And the BCOL collaboration between others has shown that we can measure it for small scale fields in solar-like stars. So the thing that we're lacking now really is the type of time series that EPRV needs to really analyze radial velocity data. And also we kind of want to start from a star that we know very well. To do this, then I picked SDO. We've been observing the sun for many, many years, and we have precise observation of the magnetic fields thanks to SDO. And by using information from the intensitygram, the Dopplergram, and the magnetogram, and using the Solaster code, we can derive time series of the model radial velocity that's shown here on top, and the longitudinal line of sight magnetic flux. Now, we have the time series, they look wonderful. The first thing to do to see if we can and how we can use the magnetic flux is to check whether they correlate or not. The answer is they absolutely do not. We are kind of expecting this anyway, because the longitudinal line of sight magnetic flux, or BL, only really maps the large scale fields in stars. So we do need to get a bit more creative in our analysis techniques. At the same time, before we go any further out, we have to realize that the type of information we get out of SDO is not really fully representative of what an RV surveys will look like, not with precisions, not with cadence or anything of the sort. So instead, let's look at something that is a bit more representative of stars and RV surveys for stars. Well, for the sun, we can look at Harps North data. It's been going on for a while, and I plot here on the top the RVs, and on the bottom, I picked one of the popular proxies that we currently use, the S-index, that I will mostly use as a benchmark for the rest of this analysis. Let's start by matching the data. For this, for the scope of this analysis, I started looking at a baseline of about 100 days, which is more or less a typical season for a star. And I've chosen to take one observation per night. Since the Harps North Solar Telescope is ground-based, it's in La Palma, bad weather is automatically included in the analysis. Then what I did, I have selected an SDO image that was closest in time to depict data point. And by the end of this, I had 4 time series: the SDO magnetic flux BL, the SDO RVs, which I don't really use more than for sanity checks, the Harps North RVs, and the Harps North S-index. To really test the efficiency of the magnetic flux, the longitudinal magnetic flux as a proxy, I have selected 3 different levels of regimes of activity. I went as high as we could using the Harps North data in 2005, at a medium level in 2016, 17, and finally at a very low activity level in 2020. And you can see the chunks that I have selected here. Before we jump in the analysis, I want to quickly address uncertainties. SDOHMI magnetograms have ridiculously small uncertainties. So propagating errors like that is just not reasonable when you're trying to emulate polarimetry. Instead, what I did, I took the optimistic 0.2 Gauss precision that was achieved by the bicolor collaboration before, and I generated white noise to this level and added it to the SDO magnetic flux to kind of even the fields between what we currently have and what we hope to have in a very nice polarimetry survey. Now, let's start by looking at high activity. This is what the chunks that I've taken look like: RV in the top, longitudinal magnetic flux in the bottom, in the middle, and S index on the bottom with error bars. This is over 100 days, and it's about 60 data points. Even by visual expansion, we can clearly see that the magnetic flux is modeled, strongly modeled by the rotational period of the star, as well as this half period signals that it's related to the distribution of stellar activity, as well as their evolution. Now, let's do the kind of basic analysis we would do in a prior detection paper. And let's start by checking the correlation. As expected, the longitudinal magnetic flux doesn't really correlate. The S index correlates really well. Next step is periodogram analysis. This is the GLS periodogram of the RVs, and in gray here, I highlight the accepted rotational period of the sun of 27 days. As we can see, the RVs do pick up the rotational period, but not to the level of FAPs that we would like to see. Next is the S index. As we've known, the S index really picks up the rotation really well. How does the polarized magnetic flux behave? We don't pick up a rotational period, but we are sensitive to the half rotational period as expected by just looking at the data. So why would we want to go any further since we know the S index behaves really well? This is because the same periodograms will not show for low activity. At low activity, the S index really does not behave as well as we are hoping to. So let's try and see if the magnetic flux, the polarized magnetic flux, can help us in all the different regimes. And at the start, I mentioned we need to get a bit more creative than a simple correlation and things of the sort. And my way of getting creative is Gaussian process regression. We've heard about this a lot. So I'm not going to really focus on this too much, but I've modeled the 3-time series separately using my code that is currently being packaged for public use, MagPi, and I've picked a quasi-periodic kernel with a white nose jitter term. And it has these 5 hyperparameters, but we don't really care about all of them. We're going to really focus on this too: the period, which is the stellar rotation period, and the evolution timescales, which maps the lifetimes of active regions. For this analysis, all priors are flat forced positive priors, which means that this analysis is very much a preliminary, uninformed analysis of the data. This is the first step that we would do in any prior detection. So how do we do? Let's do a GPU regression and let's look at the posteriors. This is what the posteriors for period and evolution timescales look for the high activity case. As we can see, the polarized magnetic flux is very well modeled by a single Gaussian process with a quasi-periodic kernel. And it nicely peaks at the rotational period of the sun, here indicated by a dashed black line. And at the same time, I want to quickly stop about time scale. Here, we've noticed that not just for this case, but consistently throughout the analysis, the magnetic flux BL's evolution timescale is larger than the one at which the RV converged to. Now, part of this can be due to the fact that the rate velocity of posterior distribution for the period is very often, if not always, bimodally peaked. So there might be some degeneracy with the evolution timescale. But at the same time, we do expect the evolution timescale of the magnetic flux to be slightly longer than the one from the RVs, because the magnetic fields that generate the kind of automatic variability that we are sensitive to in RVs endure longer on the surface of the star than their photometric counterparts. Okay, it works lovely. It's very well modeled at a high activity level. How does it do at medium activity in 2016-ish? This is our set of data, and already at medium activity, the BL is the only one that can really unambiguously pick out the rotation period of the star in a very basic periodogram analysis. The S-index still picks up the period, but it's not only sensitive to the period. But now let's see how the posteriors look like. Once again, the magnetic flux is well described by a single GP with a cadiperiodic kernel, and it does pick nice and tight around the rotational period of the sun. The real test, however, it's a low activity regime. Here, the periodograms gives us nothing. We have no correlation, not even in the S-index. And if we look at the time series, we see that our error bars are starting to get significantly large with respect of the maximum amplitude of the GPs, the BL. So G progression, how do we do? Well, we do pretty well. Yes, the magnetic flux distribution on the period is not the cleanest, but again, this is a very preliminary, uninformed analysis. This is a blind search of what that we're trying to see if we can actually see the rotation period of the sun. So throughout all levels of activity, the magnetic flux is really the only one that can give us clear information and very well modeled information from the point of view of a single GP framework. And thanks to the magnetic flux, we can clearly see the rotation period throughout all stages of activity. So I kind of want to highlight my takeaways and what my next steps will be. Once again, BL is strongly modulated by a stellar rotational period, and therefore it can be a very valuable model, proxy to model stellar activity, especially because it's mapped so nicely by a QP kernel. As next steps, I plan on trying to model the Hubble node solar data using information derived from the magnetic flux analysis and see if, what are the results of injection recovery tests. At the same time, I'm hoping to expand this analysis to a multidimensional GP framework to see how modeling RVs and BL at the same time can help. And possibly the next step ideally would be to try and get perimeter observations of other solar-like less active stars and see how we do with actual Stokes VNI profiles and polarimetry. So this is the end of my talk. I just want to say that I'll be in the job market relatively soon. And if you're interested about more regarding polarimetry in the context of EPRV, please check out the poster 19 with Belinda and the Terrantic polarimetry team. And if you're interested in more Exeter work, check out poster 95 by Ben Lakeland. Thank you very much for listening, and I'll open the ground for questions.
Fantastic, thank you. We've got a question right up here in the front, if we can get a microphone up here.
Thank you very much for very interesting results. I would like make a comment regarding HMI observations.
Yes.
Actually, HMI didn't design to measure weak magnetic fields. What it means, errors can be a little bit larger than you expect, and the same for uncertainties. But in any way, it is very interesting, and just to discuss about uncertainties, it is really a lot different reasons why it is. We can discuss about this offline, of course. It's separate talk, actually.
Another question over here, I think.
Okay, thanks for the talk. I'm maybe confused, but I thought that the longitude in the Haywood's paper, the magnetic field was strongly correlated with the RVs. Is it another?
So this is not, so the one that's very strongly correlated with the RV is the unpolarized magnetic flux.
Okay, yeah.
This is a longitudinal magnetic flux, so it's the polarized version of it.
Okay, thanks.
Xavier?
Yeah, it's a very similar question, I think, but because In the Haywood paper, it was the unsigned
Yes.
magnetic flux. So we will really measure locally. And if there was positive and negative, it was just the absolute flux. So it was not compensating for. Here you are speaking about the total one.
Yes, I'm talking about the large scale magnetic fields.
Okay.
The things, so to get the unpolarized magnetic flux, we need all 4 Stokes profiles,
Yes.
but Q and U are debatable whether we can actually measure them for solar-like stars. So this is the longitudinal line of sight, which means that only use the intensity and circular polarization Stokes profiles.
Okay, so we could get easily this one with spectropolarimeters on other stars.
Yes, hopefully.
Okay, thank you.
Need to check that. Yeah, we're working on figuring out exactly how easily we can do it with the Terra hunting experiment polarimetry team. So do feel free to come and see the poster because we do address that.
All right, let's thanks.